Yeah, so we weren't able to afford daycare, so we just watched it ourselves. Many of our friends, they will invite their parent to come over when they were actual kind of watch the kid. But we were also for our first kid, we didn't do it. So
Yeah,
see,
like that's becoming less of an option for me.
yes,
Because my, I'm a bit older, which means my mom's a bit older.
yeah. But I think it's either way. Well, people just try to find a solution when they see a problem. So there's no problem. You don't have to look for a solution.
But again, like I think the career development is again like still more how I'm leaning because I do have a house. It needs renovations. So like if I do the P and FM exams and I get into the actuary, then I'm generating enough income to where I can fix up my house. And I'd honestly like to sell it. I get it fixed up, I think. Or right now, my cousin's living with me as a roommate. And then once it's fixed up, maybe be like, well, I'm gonna be moving out, so rent's gonna be going up. And then like using it like to help out my family in like ways. Like that way, they can have a place where rent's all right, so it helps me out because I'm getting income from them. But at the same time, it's not so ungodly. I can control that to where it's not so ungodly high that they're struggling and then they can. So I thought about, trying to use that house kind of the way it's been for me for like some other members of my family to like help them to use as a launching pad for like getting their own house or things of that nature.
Hey, we're missing 2/3 of the class.
I can't believe it.
About 8.5. It's related to 7.5, but you can actually see these two are connected.
Send the email to the Golden State Foundation.
Okay. Are you applying for the?
No, I received the Arvin Phelps Memorial Scholarship like at this year's, but one of the stipulations for it is that I go full time in the fall and spring.
I see.
But I've only got 6 classes left.
I see.
So it's kind of like,
Uh-huh.
so if I'm gonna have to like take a couple extra classes to get the scholarship, then I'm probably just gonna be like, well, I appreciate the award of it, but I'm going to have to respectfully decline.
You mean next year?
Yeah. So my plan right now is to take one course over the summer, 3 courses over fall, and then 2 courses come spring. So I wouldn't be considered full-time. And one of the stipulations being the full-time requirement. And,
Email and find out.
and again, even if I don't take a class in the summer and then I load up fall, I'd only have 2 classes in the spring. It wouldn't be full-time, so I'm trying to figure out
Yeah.
like
Maybe they can.
there's extenuating circumstances that can be like brought to their attention. And then also, another thing I have to do is write a thank you card, which is fine. But, I was trying to figure out the specifics of the donor, or if they're just wanting like, do you just want the generic dear donor? Because then I feel like it's not, I feel like sending, if it's a thank you card that's being sent to a specific person, then like having their name on it's much more personal and much more like,
Yeah.
rather than just a generic kind of, oh, thank you. Like, so I was trying to figure out that as well. So, and then I've got to deal with Bank Mobile. Because, so again, it's been a while. I took the nice little hiatus from school. So I have my Bank Mobile's information for like scholarships, financial aid set up, but it's set up through a phone number that I no longer have. So I'm not being able to access the account and to like get things reset up because it's already set up. So I sent them an email and they emailed me back just like a one-time use code, but it wasn't like the code for like setting up your information. It was like a one-time use code, like that would be sent to my phone. But then once I try and log in again, I get sent another code. So that code's no good. So it's like, why did you even send me that? And then every time I've called them, I get put on hold and have to listen to this like they put the hold music on, but then like every 10 seconds of the hold music, they have like a message, an FAQ message. If you are trying to reset your password, use the following. Blah, 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 blah. That's one of the options in your menus that I had to jump through to get here.
I see.
Why do I have to listen to this again? So then 10 more seconds of hold music. If you need to set up your account, please.
Oh, well.
But I'm like, this is the worst hold ever. It's like they want you to hang up. So I'm also got to try and figure that out somehow.
Okay, I think Greg is online. You're in the class. I guess we're only missing Alex. So let's start.
All right.
So today we're gonna talk about 8.5. It's connected to 7.5. So 8.5 is distribution-free inferences. 7.5 is distribution-free confident interval. So if we have a break down now, we probably do a little. 7.5 is try to construct the interval using just the data. And so we're using the order statistic as a way to construct the interval. For example, we can have an interval for the meeting using Y1 and Y5. So that was 5 number, first number, and the highest number is there. The problem is we don't know the confidence level if we are using Y1, Y5. So we were talking about how to construct the probability calculation. You want to find out what is the probability the median is between Y1, Y5. We have the probability for any number of that distribution to be less than median. And that was 0.5. So out of the 5 number, we know the probability of 1 number lower than median. So what's the probability 5 number median between 1, 1, and 5? And that was the calculation we did in 7.5. So we would say if if meeting is between y1 and y5, so then either one of the 5 below the median, or 2 of the number below the median, or 4 of the number below the median, 1 above. So with that, we can see the first scenario is saying out of 5, number 1 below. That's what we call P1. N equal to 5, number success is 1. Assuming the probability to be below, to have below median is 0.5. So P1, P2, P3, P4, that's all we need to calculate. We end up having to reverse the process, we do 1 minus P0, P5. P0, P5 are calculated by 0.5 to the power 5. So that is 0.9375. So the percentage of confidence is 94% roughly if we use interval y1, y5. That would say using a binomial probability as a way to determine level of confidence. Right, that can be extended to sample size equal to n instead of 5. So the probability that the median between y1, yn is 1 minus 0.5 to the power n minus 0.5 to the power n. So the higher the n, the higher the confidence level. All right, and then the next of the question will be maybe instead of using the smallest number and the biggest number, we can use a less relaxed interval. Maybe it's y2 to yn minus 1 or y3 to yn minus 2. And then with that, we have to figure out a way to calculate the probability. So for median between y2 yn minus 1, 6. So we want to find probability of p2, p3, pn minus 2. Those are the number below the median. In that case, the probability is a big summation, and the idea can be extended to any interval yi to yj. So the probability for median to between yi, yj is p1, pi plus I plus 1, and then until pj minus 1. That idea, that formula extend. So we're not having a calculation. So that was the example that we had in the text. We have 9 number. We order this 9 number. We identify y2 and yn minus 1. It's y2 to y8. Those numbers creating the intermediate. Find now the confidence will take the number the basically is summation p2 to P2, P3, P5, P2, 3, 4, 5, until 7. And that's a long summation. Instead of using cumulative probability to do subtraction, and then we end up having probability of 0.9610. That's an exercise on calculating the confidence level and the confidence itself. Right, and this is a table from the book. You said you were using this table all the time. And then for different sample size, and we were able to find the confidence level and the confidence interval. That's that one. And then we can also use R to calculate the probability. For example, for probability between 1 and 7, that was size 9. For size 9 in the table here, we have when sample size is 9 for the interval between 2 and 8, we have 9610. This the calculation is we will calculate probability in the binomial distribution. This is a cumulative probability between 0, 1, 2, 3, and 2, 7. This is a probability for 0, 1. Right, you subtract these two, so 0.98 minus 0.19. That will be giving us 0.96. So it would be the same number after subtraction. It would be 0.9610 subtract these two. So that was just illustrating how to calculate those two numbers, the number 9805 and 0195. Those numbers are calculatable using R function. Right. We can also calculate the probability using normal distribution. So earlier, the P5 plus P6 plus P11 to calculate probability, the median between Y5 and Y12, we're able to use this calculation. That calculation using binomial distribution, we end up having 9232. But if we do a normal distribution, we'll take the upper bound Yeah, including 11, 5 to 11, including 11. So we would do 11.5 for the upper bound in the normal distribution, and including 5. So the lower bound is 4.5. So we have 11.5 and 4.5 and put it in normal distribution. We minus the mean, which is 8 in this question, and divided by 2. That's the standard deviation for the curve. So the after standardizing there, it would find the z value using the z value to find probability. It's less accurate, but we still get a pretty close number. Any questions? So as far as the probability, the 8 is n times p. The standard deviation is square root of nt cubed. So we use a binomial distribution formula to determine those. We use this calculation. Okay, so in general, the formula for the probability that certain percentile between yi and yj is a calculation of summation in the binomial formula. You calculate pi plus 1, pi plus 2 until pj minus 1. So a summation of several binomial probability. Each binomial probability will follow the binomial formula. Now, instead of in this calculation, the p has to be the percentile that you are calculating. So this formula applies to not just to the median, to the 20th percentile, the 80th percentile, any percentile that you want to find the confidence interval for. That was example 7.5. We're trying to find the interval for the 25th percentile. We can find a point estimate for the 25th percentile. You would take 0.25 times 28, the percentile times n plus 1, give you the exact location of the percentile. And then that would be a point. In this case, do n plus 1 times 0.25. So we know the number 7 theta is a point estimate. So from that number, we go up and below. So y7 is the center. So y7, 7, 8, 9, 10, and then y7 below is 8, 6, 5, 4. So y4 to y10 is the interval. We can find the probability, the 25th percentile between these two numbers by calculating P4, P5, P6, P7, P9, and using the probability with the binomial distribution rate, we find probability that was 0.8201. You guys probably did the homework, so this is pretty much a review, right? And then that was a normal distribution approximation for the same thing. Yeah, pretty close number. And now with the homework for 7.5. All right, today we're moving on to 8.5. We want to find a hypothesis test for the median, because in the past we have hypothesis test for one mean, it's one sample t-test, hypothesis for two mean to find out if their mean are equal. That's a two sample t-test. We also have hypothesis test for the standard deviation in 8.3. In 8.3, we have a hypothesis test for the variance. So there's a one sample variance test, and then there's two sample variance tests. So if you got one sample compare variance to one number, you would do a chi-square test. If you want to have two variance that you want to compare, then you're doing division. Variance 1 divided by variance 2 equal to 1 is H0, not equal to 1 is HA. So that's the F test instead. So these are being covered in 8.1, 8.2, and then the chi-square, the variance tests or the test for standard deviation are in 8.3. And then 8.7, we were comparing proportion. So that's a proportion test, which is a discrete data. For proportion test, we have one proportion test, two proportion tests. Both of them are in section 8.4. So pretty much this page covers most of the popular hypothesis that we're learning. Right now, we're working on in the middle. So we're not assuming for proportion test, we have a z value that we're going to calculate. For the variance test or for the variance test, we have chi-square or F calculation of the F stats. For the one sample or two sample test for the mean, we need to calculate the t-value. So now in the middle, let's say you don't assume any distribution. We don't assume a normal distribution. We don't have large sample. So in this case, we're looking at the median instead. So if the data are symmetrical, then the median will be roughly equal to the mean. So having a hypothesis test on the mean allow us to identify the center. So these are the two we'll be studying in 8.5. One is called Wilcoxon test. That is determining whether the median equal to a number. So essentially, it's kind of similar to determining the means. This is the distribution-free test that we're doing. The other one is try to compare two different data sets. Are they having the same median or are they having different medians? That's in the text is being called Wilcoxon two-sample Wilcoxon test. But it sometimes in certain book it's also called Mann-Whitney test. It's the really one sample Wilcoxon test or two sample test that we're doing today. All right, so let's say, hey, the title is called nonparametric test or distribution test, non-distribution free test. So in this method, we're not assuming we have normal distribution. So we pretty much only depend on the order statistic to determine what happened for the hypothesis test. So our null hypothesis will be the mean, like for the one sample scenario, the median equal to a number m0. The alternative is the median does not equal m0, does not equal that number. So that will be the hypothesis that we will be using in this section. So this section, the parameter is not the mean, it's m, which represents the median. So median equal to this or not equal to this. If it's one sample. If you have two samples, then the median 1 equal to median 2. That was the hypothesis. Then the alternative can be left tail, right tail, two tail. Any questions? So let's look at example. All right, we start something simple. This is not the Wilcoxon test, but we're gonna try to make it intuitively meaningful. It's called a sign test. Sign being positive or negative, big or small. Right. So let's say we're trying to test if the median equal to m0. The number. So what was the plan? Let's say you collect a bunch of number. You're gonna compare every number in the sample to this m0. Right? You want to see how many of these number is smaller than 0. How many of them is bigger than 0. So how do we compare? We subtract. So m0 is already in the hypothesis. So you're gonna have all your random sample minus m0. Now, if it's bigger than m0, then the subtraction will be positive. If the x value is smaller than m0, it will be negative. And now what do? We're gonna find out how many of them is a number of negative difference. Okay, so the y is the number of the subtraction that is negative, the negative difference. Are we okay? So if data is below the median, we will end up having negative number, and y represent the negative number in the subtraction. Are we okay? So ideally, if the median is really equal to that number, you should have half below the m0, half negative, half positive. So if you have too many negative, which means the median is smaller than m0. So that's the plan. So then this is why it's called a sign test. So we only care about whether it's negative or positive. It's a sign. So we don't know how much it's negative or positive. So that's why this test is only partial, but at least give us some idea. Now, the number of data being negative in all these deviation differences, it will be follow a binomial distribution, basically saying you throw a number there, how many of them are negative, right? Ideally, half negative, half positive. So the probability is 1 1/2, because we're looking at the median, meaning the percentage 1/2. So the y value follow a binomial distribution, n being the sample size, 1/2 being the probability. So we can see the probability of y equal to 2 or 1 or 3, the y value. It follow kind of binomial distribution there. So right now the y being what people call a statistic. So we're using y as a statistic to do this test. And if we study a statistic, then we need to know how it distributes. So what was the probability related to y equal to 1, y equal to all that? So we're going to try to look at a scenario. In this question, the hypothesis H0 is n equals 6.2, H1 is n less than 6.2. So that's why we focus on the number less than 6.2. So this is X represent the length of time in second between two calls entering a call center. So essentially, we're looking at so how long can we wait to receive a call? So it's length of waiting time on average. So then we got 20 numbers. So those are the 20 waiting time. We're trying to clock it whenever we have a call. We don't have to clock it. Whenever we're waiting on the call, we can have a clock on to see how long we wait for the next call. So get 20 number for the waiting time. So you can see all these numbers. What we're gonna do is we take all these numbers, we're gonna minus the 6.2 to say how many of them are negative, right? So only the number that's below 6.2 will end up having a negative difference. You see those numbers that are positive, we didn't really switch the color. We switch all the number that's less than 6.2, we switch it to a blue color to indicate how many of them are giving us negative number. Are we okay? So how many of them, that will be the y value. So y represents the number less time that is less than 6.2, because we're trying to find the evidence for H1. Evidence is below 6.2. We're going to find how many calls are below 6.2. It should now be 1, 2, 3, 4, 5, 6, 7, 8, 9. So among 20 data, 9 below, and the other 11 above, right? I think that's kind of fair, right? It's not that big deal, because if it's the median equal to 6.2, then there should be 10 below, 10 above, right? Roughly. But things are never exactly equal, right? Doing 10-10, you have to be like perfectly in the middle. But this is a random data collection. So being a 9 and 11 sounds reasonable. I mean, if you only have a 4 below, or so that kind of scales things. So that's my idea. So because y equal to 9 and null hypothesis is not rejected, so that's why we can kind of see the conclusion for. So using the number of data below the or high the median could be a way to run the test procedure. Any question? Okay, so this is one method. Okay, so let's review all the steps we're talking about. Assuming H0 is right, 6.2 is a median, then y follow a binomial distribution. We can calculate what is the probability of y above 14. That means we are using 14 as a rejection, boundary of the rejection. So if the number below the 6.2 is bigger than 14, like way more than 9, like a lot of calls below 6.1, that we know that median actually is going to be below 6.2. And then we can calculate this probability because it's like the number of data above 14. We can calculate this probability y above 14, which is a binomial probability. Are we okay? All right, so we can actually, for example, the P14 will be 20C14 and then 0.5 to the power 14, another 0.5 to the power 6. Right, yeah, so it's the partial 20, exactly. So then all these.
Think about these, I really like these, the 0.5.
Yes, that's why there's less computation there. So the total is 0.057. So it's really a small probability because 0.5 to 20 power 20 is a small number. So if we run, that's going to be our alpha. It's going to be the probability of rejection. If you only reject when y is higher than 14, then your probability of rejecting or alpha will be 0.5. So null hypothesis is median equal to 6.2. Alternative is median less than 6.2. So we try to find out how many are exactly below 6.2. and we know it was end up being 9. So therefore, we have a decision. We're saying y has to be higher than 14 to reject. All right, in that case, the rejection region have an area, have a probability of 0.0577. Now take a sample and calculate y. According to our sample, y equal 9, so we do not reject, right? And then because y is low, y is lower than 14. So it's saying that if there's more data below the median, we would reject. Being 9, it's not that many below. That's what we just did is called a sign test, a simple sign test. But we're going to learn what's called Wilcoxon sign rank test. So not only do we look at the sign, we also are going to rank the data. Rank the data means some are small, some are bigger. So we want to find deviation from the center, rank the data. So the assumption of the Wilcoxon test, so this has to be satisfied. Number one, we have to have a random sample of continuous type. If you have discrete data, normally we don't do this. It's just propounded the data. Number two, the density function has to be symmetrical about the meaning, meaning that if you have collect data and you present a histogram and they're roughly like severely skewed, then for the really skewed data, we should not do the Wilcoxon test. Only work for symmetrical data. Number three, no two divisions are equal and no division is meaning. That's kind of strict, meaning that none of the data are exactly equal to the number that in your hypothesis, and none of the number are exactly equal to each other, right? And that's a little bit difficult, but we can actually fix it. So we can fix the ranking. The non-equal part. So the condition number 3 will often have to treat. We change our data in order to adjust it. So exactly what we do, let's talk about the plan, which is like we're not calculating how many below, how many above. We're actually going to look at rank the deviation. So you're going to take a random that's in order to test the hypothesis of the meeting equal to a M0 number. We're going to have a random sample. Then we're going to take the random sample minus the median. That's the same as earlier. But this time we're going to find the deviation distance. We take the absolute value of all the deviation, x1 minus m0, take absolute value, x2 minus m0, take absolute value, and now we're going to rank them. We're going to sort them in an ascending order. We're going to sort them, and then this time it's called sign rank. The rank are going to be integer, right? 1, 2, 3, 4 is going to be the ranking. So we're not using the actual number like 5 minus 5.6. We're not finding the exact number. We are only adding the rank. So the statistics are going to be integer again. So we're not, you know what I'm saying? We're not taking the raw number, even though it's for continuous data. We don't do the number, do the ranking. So RK represent the rank of xk minus m0, and then it's called sign rank. We're gonna add sign to it. All right, so basically R1, R2, Rn is going to be a permutation of the n number, and now we are going to, for every RK, we're gonna add a sign to it, the sign of the differences. So if xk is bigger than m0, then the rank is positive. If mk is smaller, negative, and xk minus m0, we take up the value earlier, right? Because then line them up, find out the absolute value, big or small, and then we rank them. After ranking them, the one that's negative big, we put a negative sign to it. Are we okay? So we add a sign to the ranking, and we call that Wilcoxon sign rank. And so that's the W. We will have all the sign rank added together. So it's called Wilcoxon summation of sign rank. We add up all the sign rank, and that's our statistic. It's called W. Any question? So that was a plan. It's kind of different from the R coding though. R has its own Wilcoxon function, but doesn't have the same Wilcoxon as we were doing this section. We kind of have to differentiate From the R coding, we can't rely on the R coding 100%. So we kind of have to do our own calculation there. So here is a numerical example. Let's say we have 10 number. If that 10 number, what we're gonna do is we are testing if the meeting equal to 3.7, right? And then the alternative is meeting bigger than 3.7. So what we're gonna do, we were calculating what we call a W. So number one, every number, I call it xk minus 2.7. So these 10 number will subtract 3.7. We end up having a bunch of number. You can see after the subtraction, some are negative, some are positive. And then we're gonna take the absolute value. Now they're all positive. Now we're gonna rank them. So we didn't change the order. We should change the order, which the rank will be 1, 2, 3, 4, right? Now, since we didn't change the order, the rank looks like 5 at 1. I mean, the smallest one is 0.2, that's rank 1. And the second number is the 0.6. So the ranking will be 2 there. So anyway, after the subtraction, what's the order? I felt like some of the number are like additional there. These are fine. Okay, so I found like some of them are extra. This is not making sense. That's right. So last number is a 0.6 there. So the 0.6 is supposed to be the rank 2 there. Are we okay?
There's a -2 before the 0.6, so you should have a 2 in the absolute value. Like between the 1.1 and the 0.6, shouldn't there be a 2.0?
Right, there's a -2. Yes, right. So there's a 2. After the X value. So 1, 2, 3, 6. These are all ranking. So after we rank the absolute value, and then we're gonna look at each one that was negative, we make the ranking negative. So there's -0.9. So we have -3 there, and there's a -2, -1, there's -1, -8. So the ranks are integer. We add the negative sign to those integer that has originally a negative rank. Are we okay? All right, so finally we will do a summation. So we add all the signed rank total, we end up having a 25. So you can also look at all the ranking. Most of the ranks are positive because most of them there's a more positive deviation than negative one. So then we end up having a large number of 25. I think we will reject the non-analysis. Oh, is it reasonable? So that's really the calculation for the assigned rank. Are we okay? And that's what we're gonna try to practice. In here, we have an example. It's what I'm gonna do today for attendance. So here we have similar scenario. What is the assigned rank sum? So we're trying to find a summation here. And let's try and see how it works. Initially, you want to record your data. You can also have a pencil ready for the calculation. Since we have R, we have an easy way to do the sorting. So X equal to C, we are starting from 1.12 and 1.13 and 1.19, 1.25. 06.31. This is a larger data set, 1.23, 1.29, 1.17, 1.20, 1.1, 1.18, 1.23. It says we have, let's see how many number do we have. So let's see what's the size of the data. And I'm gonna use the computer to help me rank them and also to sort the data easily. So this is our data set. Let's see how many numbers we have. Okay, and was there anything wrong? Okay, there's supposed to be a column. Okay, so we have 14 number. Let's say if it's true, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 14. Okay, so let's see how we are trying to compare with the 1.14. So what we're gonna do, we x minus 1.14, which then give you the deviation. So try to do the same thing that was in the text, but we're doing it together. Larger. So after the computation, we see this, and you kind of see how many negative, how many positive. I cannot tell how negative looks like. There's more negative, more positive than negative.
It's like 5.
Okay, but the question is to do a signed rank. So let's say we're gonna rank these, but we're gonna rank the absolute value. So there's a function called rank, and absolute value of x. We should sort it so it's easier, right? So I'm gonna do y equal to this. Wait. So then the rank will be like 1, 2, 3, 4 instead of having it. Oh no, we should sort the absolute value is x. So what do we do? X minus 1 point. I feel like 1.1. Should we rank it or not? So let's. The book didn't rank it, did not sort it. Maybe we'll just leave it that way. This is the one with the sign, and this is the one without the sign. All right, and then we're going to rank the one without the sign and add a sign to it. So if we do it this way, this. Oh, doesn't accept the absolute sense. So ABS, the absolute value. All right, I think that should work. Look at the absolute value and then ranks the absolute value. All right, so you can see the one with the sign because negative sign takes space, and this is a line, the 14 number without the sign. You can see the order. Smallest number is 0.01, and then the number 2. There's a 2.5. Okay, so why is it 2.5? Because we have 0.02, another 0.02. So when the number are ranked the same, we have to force them to be the same rank. Originally, it was supposed to be there's 1. It was averaging between 2 and 3, right? Originally it was 1, 2, 3. So the 2 and 3 are equal. Therefore, they shouldn't be ranked differently. They're both being called 2.5 instead of 2 and 3. You got 2.5, 2.5. Are we okay?
Kind of different outcomes.
Which one?
Like I have 3.5 rather than 2.5.
Okay, was it the raw data that has to?
That's what I was kind of looking at. It's just like go back, trying to compare,
Uh-huh.
see
Yeah.
what I entered wrong. Yes.
Oh, you can read yours, I can read mine. If we read this in time, can we find it?
Alright, so I got
1
12,
point?
I was just gonna say the
Okay.
decimal, so I
Okay.
got 12, 13, 19, 25, 6, 06,
Uh-huh.
31, 12, 23, 29, 17, 20, 11, 14.
It's, this one.
So it's supposed to be 18. That will make a difference.
It's 18 there. Okay, so basically this allows to have the rank, basically, or have the rank function that ranked it for us. Otherwise, we'll have a hard time ranking 14 number by hand. Are we okay? So now we want to add the sign to it because we need to add the sign rank. So what is the sign rank? We would sign the one that's in x minus 1.14. The x minus 1.14 have a sign, but we multiply the sign to the rank that we are getting there. So this is what we will do. We take that one, it's actually a vector, we multiply with the rank, and that will creating a rank multiplied with a sign. So end up getting this. So when we write that, you can see, and I have the original number in there. You can see the one that's negative now have a negative rank to it. And there's negative 0.08. I'm giving this. So all the one that was negative have a negative rank. It's a negative 0.02, negative 2.5. Are you okay? So this entire thing, the entire lecture is called the signed rank, right? And then we want to have a summation. That's why maybe we should give it name, right? So this is a signed. That name is a little long, but now we put the signed rank into a word that's called signed rank, and we find the summation of the. Maybe I should pick a shorter name. And you can just basically call A equal to the whole thing, and then it will be a summation of that you want to get less. Writing a longer name have the danger of misspelling the name and the summation inaccurate. So essentially, we're adding the entire vector with the sign, of course. That's our sum. Once you put them into the signed rank name, it doesn't display it anymore. Only the summation is displayed. Are we okay? So I hope that kind of makes sense. So I'm trying to illustrate how do we exactly do the signed rank thing. So the answer should be a 67. Gregory, are you online? Are you able to answer? Let me turn on the scanner. The scanner is not on yet earlier. Now we're just we're using that one for the attendance. Let me turn this on. Okay, so the final answer should be a 67 as we were doing together. And this is basically the process how we handle the Wilcox test. Because it will be identical to the Wilcox test. R has a Wilcox test, but it has a slight different answer. The final conclusion should be the same, but it's not the same number. W in R is not the same. Right, so we're just talking about how to calculate the signed rank here. Now, how do we, and that was that example, same example in this page. we got all those raw number. How do we do it with R? Take all your raw data. You minus say 3.7. Want to say if the mean equals 6.7, so you see some negative, some positive. I use the Y. The Y can be displayed, and you can do the rank of the absolute value of the Y, right? And then you can display the rank. And then I take the rank, the sign of Y, multiply to the rank. Rank is being the rank vector. So the rank vector multiply the sign vector, creating the sign vector. We call sign. Then W equal to summation of the sign. So it's the same process we're doing with the R. So that's how you can calculate the sign sum in R. This is the R function called Wilcox dot test. And you put in your data, you can put in the mean equal to 3.7 and calculate it. It will display a B equal to 40. So RW, it was 25 in this example. So it's not equal to 40. However, if you look at those signs, all right, and you only add the positive number, so 5, 1, 6, 7, and then 9, 10, and then 2. If you only add up the positive, the sign rank, it is 40. So if you try to think about the connection, what we're doing, we still do it. Instead, in R, it doesn't add the negative sign. It only adds the positive sign. And we are having that 40. The p-value is 11.11662. All right, so let's talk about how do we understand. So once we find the W, is the W high or is the W low? We kind of have to know what was the distribution of W. Right, knowing the W doesn't mean we know the probability. We have to find the probability relate the W. That way we can compare with alpha or compare with the critical W. So here we are. Now, in order to identify critical region, we have to know how high W is. If it's a left tilt test, you have to have a lower boundary, W lower than C2, then it's in the rejection region. If you do a right tail test, then W has to be higher than C4. So we're trying to find a proper boundary to mark the rejection region to compare with the W. So we need to know a little bit more about exactly what W is behavior. So what exactly is W? If we think about it, W is a summation. So summation of a bunch of smaller ones. Let's call each one of the smaller one being the X case compared to M0. So each XK, I mean the X1, X2, Xn, HK, it could be bigger than M0 or below M0. If M0 truly is a median, then probability XK below 0 or bigger than M0 will be 50%. So it's 50% positive, 50% negative for every number. So it's one way or the other. In that case, W will be a summation of all these 50 per 50 kind of situation. Now for every rank, so the one that ranks number 1, it could be a positive one or negative one, being positive above the sequence above the M0 or below. The rank number 2 could be a positive 2 or negative 2. The rank number 3 could be positive 3 or negative 3. So we can think of a W as a summation of several random variables. So W have similar performance as V, assuming V equal to summation of VK. VK being the rank K. For example, V1 is one that rank number 1, and V1 equal to if V1 equal to a positive 1 or negative 1 with 50%. So the VK is the one that rank K. The rank K case number in the order statistic. It could be negative K or positive K with 50%. So VK could be positive K or negative K, either way, half chance. So that V itself is similar, is comparable to the W. Because V is a summation, W is also a summation, right? W is summation of the assigned rank, being every one positive rank or negative rank. So then we can have something to compare to. The reason we want to compare this to, because we want to make W comparable to V, and V is easier to determine the mean and variance. Right, once we know the mean and variance, we can put it into a normal distribution setting. You minus the mean and divided by the standard deviation, you have a z value, right? So our idea is let's find out, can we put a normal distribution understanding of the W? And the answer is that when the sample size is large enough, we can do that. So the expectation of the W, for every VK, the expectation is half the chance is K, half chance is negative K. So the K, the value times probability, the total is 0. So on average, the expectations for every VK, the mean equal to 0. Now the variance is equal to, variance of VK is equal to the expectation of the E of a V squared minus the square of VK. Now square of the expectation equal to 0, so just E of VK. E of VK is negative K squared times 1/2 plus positive K squared times 1/2. Basically, it's K squared. K squared will be the variance. Then what about the actual V? V is summation of the VK. So because every VK has a mean 0, the total summation of those VK will also have a mean 0. So mean is the 0 period. So what about the variance? Variance for V will be, it will be variance summation of all the individual variance. Each individual variance is K squared. So the total variance for V or W will be summation of the K squared. So it's 1 squared plus 2 squared plus 3 squared plus 4 squared until n squared. So that's the variance. And then this is a summation square in the algebra. We got a formula. So then turns out we have a variance formula for the W. Any question? So now that C, that's the number we're using to convert it into the Z. So according to central limit theorem, when the n is large enough, and mostly if we assume n is large enough, so we will have Z is equal to W minus 0 divided by square root of the variance. That was summation of square. So it's approximately normal, so we can actually find out the Z value for the W, and therefore using the normal distribution to find the probability. That's the idea. So really remember, try another example. For this question, we have the raw data, right? And then we have all the raw data minus the mean, the median. The median is 160. We have all the number minus 160, take absolute value, rank them, and then multiply the sign of the rank. And this is a sign rank. For example, see, was it already ordered? It's not. It was ordered in here, this page. But in the next page, we have the number already ordered. This is every number minus 160. And then we put it here. So this is a deviation. Some of them are negative. The negative one have an underline, had the line underline when it's negative. So we have 1, -2, 3, -4, -5, 6, -7, and 8. So they're the ranking, and that's where that summation comes from. And then the total summation for the W is summation of the signed rank, which goes 60. Are we okay? We can test it ourselves. We can do our own calculation to confirm. All right, so once we have that, we want to find the p-value. If this is a right tail test, okay, the hypothesis says median bigger than H1, the hypothesis says median bigger than 160. So it's a right tail test. We end up having a 60, we want to find the p-value for 60. Probability W bigger than 60, we convert it to a Z value. So 60 minus the mean divided by square root of the, that would be the square root of the total variance. This, the denominator is summation of n squared when n was, what was the sample size there? It was 16 number. This is a -1 because the W is an integer. We have to do a correction of continuity. So W, in order for W to be bigger or equal to 60, so we were calculating W bigger than 16 minus 1. that was the textbook solution for this. Any question? Oh, okay. So that -1 there, I think is because of continuity thing. W being an integer, but then we're converting it to a z value, and d is for continuous distribution. Right, so that set of data, I copy over the raw data, the same data for the example that we're talking about. We subtract the 160, which is a y value, and you can display the y. So this is subtraction, and save it in y, display the y, and we can find the x value y and rank that. That was a rank. We can then find the sign of y and multiply to the rank. That's the signed rank. W equals summation of the signed rank. See that W equal to exactly what we have, and it was 60 in this example. So it should be 60. And then you're gonna find the n, because we have to have the n times n plus 1 times 2n plus 1 over 6. So that was a variance calculation. You need the n values. N equal to the length of the data. And z value is w minus 1 square root of the summation, square root of that. That was a variance of the w. So this is a positive z, so 1 minus probability below z, give you the probability on the right tail, and that was p-value. It would be the same p-value as we see in the R test. Any question? All right, I think this example, I kind of already copied it over on church view. It was signed right. Is it not the same? So okay. Sorry, oh, that wasn't not the same, but it has some coding related to this set. I was doing the same thing, but I was using a different set of number. So that was the example for comparing the meeting with one single number. This is called one sample Wilcox test. Any question? So this is about some of the treatment that we already mentioned earlier. What if you have, I mean, the Wilcoxon test requires that not having any data equal to M0. So in this case, what if your random sample have data equal to M0? In that case, the subtraction end up being 0. So if it's equal to 0, we actually will delete that number. And then what if some of the number having the same number, absolute value of the difference is equal to the same number? What do we do? If they're equal, we'll averaging the rank. Okay, so we will assign the average of the corresponding rank.
So like 2.5.
Yes, for example, the second number and the 3 number equal to the same number. In that case, instead of having rank 2 and 3, we rank them as 2.5 and then 2.5. So essentially their summation stay the same. Now, what if you have 3 number, like a 2, 3, 4, they all equal to the same number. In that case, the total rank will be, that's 9, right? This is
So they all
9.
go to 3.
So 9. So they're all ranked as 3, 3, 3. Yes. So we are trying to guarantee the total summation stay the same, but we are ranking them the same way. But then maybe some of them are negative. We never know. We're ranking. It's the absolute value, right? Yeah, exactly.
It's just why you get the vector multiplication.
Right. So that's how we treat the special scenario. What if the condition number 3 is not satisfied? If it's equal to the median, then we remove it. If it's a different number that equal but not 0, then we average the rank. Oh, this example is okay, so this is the one I had on the jury review. is talking about doing the Wilcoxon sign rank statistical test if the median equal to 0. So you can see in this example, some were negative, some were positive. So the H0 had median equal to 0. H1 had median bigger than 0. So the total is 26 number. We ignore the one difference that equal to 0. So one of them is 0, we will just remove it. Then we only have 25 number, and then we rank them. And some of them are tied, so then we average the rank. Here we are. So after ranking them, then we have 0.04, 0.04, and there's another 0.04. So that was the 1, 2, 3, and that's 4, 5, 6. So originally they were supposed to be 4, 5, 6, but since they're equal, we would do this is 15, 15 divided by 3 will be 5, 5. So instead of 4, 5, 3, you have 5, 5, 5. And the thing is, one of them is, two of them are negative, so it's 5 and then -5, -5 for the ranking. And the rest of them, they're the same. Okay, and so then we find out their sign rank, which is the second row and the fourth row. We add it together. So these are the calculation. So we'll add up the sign rank. There's 2.5, 2.5, and then 5, -5, 1. And if we want to find the probability, we'll take the total sign rank. What was the p-value? P-value is probability W bigger than 51. So we'll do 51 minus 1. Again, that minus 1 is for correction of continuity, divided by 25 times 26, not 51 over 6. And then that will calculate into a Z value of 0.673. And then using the normal distribution, we will find the probability is 0.2505. That's not very significant, right? P-value only when it's small, it will be significant. So we would not be able to reject. So then it looks like the mean is roughly 0. Any question? All right, and then again, I remember I have the coding on George View. Maybe we can use those code to run the procedure. Let's see how it works. So we have the out. All right, so we have those are the data. And then when I was doing it, I actually sorted in order. Now we can easily see how it works. So this is sorting the X value. And so have it in order, and then we find the X value. We want to compare with 0 and sign the rank multiplied by the sign. I did remove the 0. There's only 25 number in there. So n equal to the length of the data, and we calculate W minus 1, W minus 1. W was 51. Okay, so then if we run this, not all the commands are mistakes in there. And let's see, we got the rank. These are the rank. The 51 was the W, so that was the output. And the Z was this is the Z calculated. So you can see we have the same p-value, right? The p-value is the 6726. That was the p-value, and then the Z was 0.67. That was the p-value is 0.2505. So we have the 0.2505. I guess the only one that will be wrong is this one. Let's see. Which part is wrong? I was using the Wilcoxon function to find out. It did. So this is a Wilcoxon sign test with R. It does have continuity correction, but you see the p-value is 2505, exactly as what we have on the 25. So we have identical p-value, except we have a W that was 51. Just like we have here, the W is 51 at the Wilcox Sandrick. So I assume that this B is a statistic in the R coding. That should be the summation of the positive rank. So if you go back there and check, it should be the same. And again, because the p-value is high, we will not be able to reject the H theorems. Let's see. All right, so that was the coding that we just did, and let's talk about what if we have two different samples, how do we compare their median? So essentially, this is called Wilcoxon rank sum test for equality of two distribution. So it's also being called Mann-Whitney test. Essentially, the two sample Wilcoxon test is the same as Mann-Whitney test. So the idea will be we have two different samples. The sample one is called X1, X2, Xn, and then sample two is called Y1, Y2, Yn, Y. Right, so two different samples, they have different sample size, and maybe they have different median. Whether they have different median or not, we're testing the equality of their median, and we put them in increasing order. So what we're gonna do is we're actually gonna combine them, right, in increasing order. That means we were supposed to sort it or rank it. After we rank it, we want to assign the average of the rank for the type value. So that would say, suppose some of the number had the same value, then the ranking will be the average. So if you have one is rank 4, the other one is rank 5, if they have the same value, it will be 4.5, 4.5 for both. So W equal to summation of ranks of X1. So you will only find out of the combined rank data, we find out summation of the rank for the X data. That's what we have W. So that's our test statistic. So supposedly, if most of the X values are higher, then the total summation of the rank will be bigger, right? If W is really, really high, then we will confirm that. Well, if W is really, really small or really, really high, then we know they're not equal. If W is roughly, so ideally you will compare the total summation rank for X data and the total summation rank for Y data. I think compare those two would be more meaningful. I assume both of them will be really high, summation of the rank. And so that will be the idea, and then at least in this text, what we in the summation of X number. So now in order to make it median, we kind of have to compare what was the average value. Assuming the median are equal, right, assuming they're actually equal, then what will happen will be the mean and variance for the W. I mean, the W that we just see that we need to know is distribution. The mean is equal to NX times nx plus ny plus 1 over 2. So that's the mean value for W. If you have the Y data summation of their rank, and the mean for the total summation of rank for the Y data will be ny times nx plus ny plus 1 over 2. So then, depending on what we are calculating, that's the first number in the calculation of the mean. But okay. Now, the second one is a variance. It says a similar formula as before for the summation square. So the variance for W is nx times ny multiplied by nx plus ny plus 1. So symmetrical about x and y because the variance of the distribution should be the same for x and y. So they have the same variance. So we can calculate what's called a Z value for W. So after knowing the W minus the mean of W divided by square root of variance of W, and I will approximate it using a normal distribution. Any question? So that was the idea. I mean, this way, having a Z there kind of give us the idea whether the W is really high or really low. I mean, you got to compare with all mean value there. So we have this. This result is actually pretty complex. We don't have the proof of it. We were just using as a given conclusion. So here we have two different set of data. We are trying to determine whether X has a higher median or Y have a higher median. So the null hypothesis assume they're equal in median. The alternate have X has a lower median than Y there. And therefore, this is a left field test. We probably get a W that has a negative p-value. So here are the calculation. We're having all the data, put it in one big set. And then you're gonna find out the total summation of ranking of the X data. Right, in that case, we are, we're in this setting, we're actually gonna combine them and rank the whole data set. And those are the rank of the X data. All right, and then we can calculate the probability. What is the p-value will be probability W below 49. You're going to take the 49 minus the mean divided by percent division computation. See. So here are the coding for the calculation. We have the X data, we have the Y data, and then we creating a new set of data, calling it new, which is really chain them together, meaning that the first half is all the X data and the second half is all the Y data. Are we okay? You can find out how many X data using the length. Length of X is in N, length of Y is in M. All right, now I need to rank the new. The new is a data set. Data set is called new. Rank the new and calling it rank. Now, in the rank is a vector that do not contain the original data. It only contains like 1, 2, 3, 4, 5, the ranking. Are we okay? So maybe not in that order because we didn't separate the order. We didn't sort it. We're maintaining the same order, but we are ranking. So now they're in the rank. You see a bunch of integer with ranks, and now we are adding the summation of the rank for X data. Remember, X is in the 1, 2, 3, 5, N, and then Y is in the N plus 1, N plus 2, N plus until N plus N. So the rest of the data set, this new is like a vector, right? The first few element in that vector is all the X data, and the rest of the vector component are the Y data. So essentially, we will identify in the rank, there's no sign this time, there's no only the rank. So the rank is a vector element from 1 to N, we're adding it together. So that's our W. Because in the W, we only want to add all the rank for the X data. So that's our W calculation. So W we plus 0.5 to do a correction of continuity because W is a discrete random variable. Because it's discrete, we put plus 0.5 to make it higher. Find probability. That's the z-value calculation. This is a n times n plus 1 over 2. That's the mean for W. The denominator is square root of the variance of W. That was our mean calculation. And that's calculated. With that, we should be getting the same value. The z is actually negative 1.43 in here, and you can check that coding yourself. And then z less than that, z, we will find out the p-value of 0.26. And that seems to be significant if the alpha is 5%. And again, if the alpha is 1%, that won't be significant. Any question? So this is what's called the two sample wave test. Again, R has a similar code. So I assigned the homework for 7, 10, and 16. Most of these are even number question. Number 7, you probably can find solution in the text. So for even number question, I want to provide some help. So I write the solution for, copy over the solution for number 10, just to give some idea. So those are the original data, X data, and the Y data. And then we want the X number, the X observation. Those are the X number, and down here are their ranking. So we're adding 1, 2, 3, 5, 6, 7, and 10, 11, 12. So all the ranking for X added together, you're getting the 107.5. Some of the ranking are the same, I guess that's why they're 0.5. So there's 20.5 there, that's why the total summation have 107.5. And then you will minus the mean divided by the square root of the Z value that seemed to be significant. So that's pretty much the reason we repackaged there. So I did provide a solution for question 10 to kind of compare to the rest of the question, the question 10, the 16 and question 4 has similar to, but not exactly the same. I also provide some coding with R, so hopefully it's not too hard to do. You can also use R to help you sort or rank. I didn't use R in this example for question 10. That was just from the question bank and pulled out the solution there, but it's pretty clear how it's run all the X number and the Y number all together sorted. And so you can see the ranking is 1 to 24, but the X number are being underlined. Right, so that's one way to do it. You can also do not sort it, but keep the order. When I was doing it with R coding, I decided not to change the order we had the ranking. That's 8.5. I hope it was okay. And using the Wilcoxon test, it's relying on the sorting and ranking for the data sets. That's it for today. If you have any questions, let me know. Oh, Wednesday, we've done the hypothesis test for 8.1, 8.2 last Wednesday. So this Wednesday, I'm going to do 8.3, 8.4. So the quiz will be over 8.3 or 8.4. 8.3 is hypothesis test for the variance. 8.4 is hypothesis test for the proportion.